The National Electrical Code, or NEC, does not mandate that a Doorbell transformer be placed on its own dedicated circuit breaker. NEC Section 210.52 code addresses overcurrent protection and states that conductors must be protected against overcurrent in accordance with their ampacity as outlined in Table 310.16 through 310.86. This means the current carrying capacity of the conductor determines the level of protection needed. The NEC further clarifies that conductors having an ampacity exceeding the value specified in Tables 310.16 through 310.86 must be individually protected based on their ampacity. However, there is an exception to this rule. Conductors and circuits not exceeding 8 feet in length between the circuit breaker or fuse and the appliance or device they serve are permitted to be unprotected, but only if they serve the single appliance or device. Now consider Section 210.52c2, which discusses the number of overcurrent devices on a single circuit. It states that no conductor should have overcurrent protection that operates at less than the conductor's ampacity unless the conductor is protected by other overcurrent devices in series with it. This limitation does not apply to conductors protected by supplementary overcurrent protection as described in Article 240, Part Roman 9. In the context of Doorbell transformers, it is essential to recognize that their ampacity is typically low. It is uncommon to encounter a Doorbell transformer wired with conductors larger than 8 American wire gauge or AUG. Consequently, Doorbell transformers generally do not necessitate dedicated overcurrent protection. To recap, the NEC stances as follows. Firstly, conductors must be protected against overcurrent based on their ampacity, as per NEC tables. Secondly, there is an exception for short conductors serving a single appliance. Thirdly, conductors should not be overprotected. Finally, Doorbell transformers rarely require dedicated overcurrent protection due to their low ampacity. Article 240 contains general requirements. It covers overcurrent protection devices, such as fuses and circuit breakers, and their application. Article 240, Part Roman 9 provides information about supplementary overcurrent protection. Table 310.16 provides ampacity ratings for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 current-carrying conductors in a raceway or cable or earth directly buried, based on ambient temperature of 30 degrees Celsius. For example, if you are using 14 AWG copper, and you look at the 75 degrees Celsius column, the ampacity is 20 amps. If you are using 12 AWG copper, and you look at the 75 degrees Celsius column, the ampacity is 25 amps. If you are using 10 AWG copper, and you look at the 75 degrees Celsius column, the ampacity is 30 amps. Conductors must be protected against overcurrent in accordance with their ampacity. Overcurrent protection is a critical aspect of electrical safety. It involves using devices like circuit breakers and fuses to protect electrical circuits from excessive current, which can lead to overheating, damage to equipment, and even fires. The National Electrical Code, or NEC, provides comprehensive guidelines on overcurrent protection to ensure the safe and reliable operation of electrical systems. Conductors, which are the wires that carry electrical current, have a specific ampacity, which is the maximum amount of current they can safely handle. This ampacity is determined by factors such as the conductor's material, size, insulation type, and the ambient temperature in which it is installed. Exceeding a conductor's ampacity can cause it to overheat, potentially damaging the insulation and creating a fire hazard. To prevent this, the NEC mandates that conductors be protected against overcurrent using overcurrent protection devices, or OCPs. These devices are designed to interrupt the flow of current when it exceeds a predetermined level. The NEC provides detailed tables, such as Table 310.16, which specify the ampacity of different types of conductors under various conditions. These tables are essential for selecting the appropriate size of conductors and the corresponding OCTs to ensure proper protection. The size of the overcurrent protection device, such as a circuit breaker or fuse, should be matched to the ampacity of the conductor it is protecting. For example, If a conductor has an ampacity of 20 amps, it should be protected by a 20 amp circuit breaker or fuse. In some cases, it may be necessary to use a smaller overcurrent protection device than the conductor's ampacity. This is permitted when the conductor is part of a motor circuit or other application where the starting current can be significantly higher than the normal operating current. In these situations, the overcurrent protection device is sized to protect the conductor from sustained overloads while allowing for the temporary high current draw during startup. The NEC also addresses the location and accessibility of overcurrent protection devices. They should be readily accessible and located in a safe place, such as an electrical panel or a junction box. This allows for easy inspection, maintenance, and replacement of the devices if needed. Overcurrent protection devices are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds its normal operating level but remains within the conductor's ampacity. Short circuits, on the other hand, occur when there is a direct connection between two conductors with different potentials, resulting in a very high current flow. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overload or short circuit occurs. They can be reset manually after the fault has been cleared. Fuses, on the other hand, are one-time devices that melt and break the circuit when an overcurrent occurs. They must be replaced after they have blown. The NEC requires that overcurrent protection devices be properly labeled to indicate their ampacity and the type of circuit they are protecting. This helps to prevent confusion and ensures that the correct device is used for each circuit. The NEC also addresses the use of supplementary overcurrent protection devices. These devices are used to protect specific components or appliances within a circuit, such as motors, transformers, or electronic equipment. They are typically smaller than the main overcurrent protection device and are designed to provide more precise protection for the specific component they are protecting. Proper overcurrent protection is essential for electrical safety. By following the guidelines in the NEC, electricians and electrical contractors can ensure that electrical circuits are properly protected from overloads and short circuits, reducing the risk of electrical fires and other hazards. In summary, the NEC requires conductors to be protected against overcurrent in accordance with their ampacity. The NEC provides detailed tables specifying the ampacity of different types of conductors. The size of the overcurrent protection device should be matched to the ampacity of the conductor it is protecting. Overcurrent protection devices should be readily accessible and properly labeled. Supplementary overcurrent protection devices may be used to protect specific components or appliances. The purpose of overcurrent protection is to protect electrical systems from overloads and short circuits. Table 310.16 is used to determine the ampacity of conductors. A circuit breaker is an electromechanical device that automatically interrupts the flow of current when an overload or short circuit occurs, and a fuse is a one-time device that melts and breaks the circuit when an overcurrent occurs. In addition to the general requirements for overcurrent protection, the NEC also includes specific requirements for certain types of electrical equipment and systems. For example, the NEC has specific requirements for the overcurrent protection of motors, transformers, and generators. These requirements are designed to protect these types of equipment from damage due to overloads and short circuits. The NEC also addresses the overcurrent protection of branch circuits and feeders. Branch circuits are the circuits that supply power to individual outlets, lights, and appliances. Feeders are the circuits that supply power to branch circuits. The NEC specifies the minimum size of conductors and the maximum size of overcurrent protection devices that can be used for branch circuits and feeders. These requirements are designed to ensure that branch circuits and feeders are adequately protected from overloads and short circuits. The NEC also addresses the overcurrent protection of control circuits. Control circuits are the circuits that are used to control electrical equipment, such as motors, transformers, and lighting systems. The NEC specifies the minimum size of conductors and the maximum size of overcurrent protection devices that can be used for control circuits. These requirements are designed to ensure that control circuits are adequately protected from overloads and short circuits. The NEC also addresses the overcurrent protection of fire alarm systems. Fire alarm systems are designed to detect fires and alert occupants of a building. The NEC specifies the minimum size of conductors and the maximum size of overcurrent protection devices that can be used for fire alarm systems. These requirements are designed to ensure that fire alarm systems are adequately protected from overloads and short circuits. The NEC also addresses the overcurrent protection of emergency systems. Emergency systems are designed to provide power to essential equipment during a power outage. The NEC specifies the minimum size of conductors and the maximum size of overcurrent protection devices that can be used for emergency systems. These requirements are designed to ensure that emergency systems are adequately protected from overloads and short circuits. The NEC also addresses the overcurrent protection of hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. The NEC specifies the types of electrical equipment that can be used in hazardous locations and the overcurrent protection requirements for this equipment. These requirements are designed to minimize the risk of fire or explosion in hazardous locations. The NEC also addresses the overcurrent protection of swimming pools and spas. Swimming pools and spas are areas where there is a risk of electric shock due to the presence of water. The NEC specifies the types of electrical equipment that can be used in swimming pools and spas and the overcurrent protection requirements for this equipment. These requirements are designed to minimize the risk of electric shock in swimming pools and spas. The NEC is a comprehensive set of standards that covers all aspects of electrical safety. By following the guidelines in the NEC, electricians and electrical contractors can ensure that electrical systems are properly installed and maintained, reducing the risk of electrical fires, electric shock, and other hazards. It is important to consult the latest edition of the NEC for the most up-to-date requirements for overcurrent protection. The NEC is updated every 3 years to reflect changes in technology and best practices. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to check with the local authorities to determine the specific requirements for overcurrent protection in your area.